Basically, what we're doing is we're starting from scratch on this change detection piece, and our raw material is the standard Landsat 5 and 7 products that we get off of the AROS Landsat processing system. Our project goes through a scene selection process. We check the image geometry. When we order these scenes from our standard process, they are supposed to be geocoded and terrain corrected to be within 1 pixel of accuracy, so under 30 meters. But we check that anyway because there's sometimes, sometimes in an automated processing fashion that just doesn't happen. We then take those products and we change them to either top of atmosphere reflectance or surface reflectance corrections to try to, in a sense, it's kind of a first-order normalization of the scenes for things like sun angles and things like that, and in theory, the atmosphere. We take an attempt to mask the clouds and the cloud shadows the best we can. We determine a common output frame for our stack. We go into Albers because our project works in Albers, and so does almost anybody else in continental wide land change. Then we run our change detection algorithm, which I'll show you about a little bit. And of course, we have the Landsat 7 SLC off data gap regions to deal with, but also the regions that we mask due to clouds and cloud shadow. What I just described is an automated process with the exception of scene selection, and that leaves us with a set of raw change parameters that our analysts then clean up and label. Now, when we ran this before, we ran with something called the VCT, or the Vegetation Change Tracker. And this thing is doing pretty much the same thing. There's a little more cleanup to do because the change detections are a little more raw than what VCT gave us. But VCT also was active pretty much over forested regions, and it masked out a lot of the other regions. And so it was leaving us wanting a little bit. The other thing that's going on there is that VCT needed a stack of 2 decades worth of imagery, and we've shortened our stacks here. First, I'll quickly talk about the surface reflectance corrections we're doing. The LANDFIRE updates are, the scenes are being processed, corrected for surface reflectance to try to correct for these sun angles and our sun distance differences. These are computed using a software package that was put together between NASA and the University of Maryland called LADAPS, and we run it on a local system here. As a footnote, we have some projects going here at AROS that are allowing us to run these base level climate products, if you want to call them that, in a very efficient manner. And so the processing for this round of LANDFIRE has, for the continental U.S., about 4,500 Landsat scenes, and they were able to process them to this level, to this surface reflectance level, in under a week, using about 200 computers. We'd still be cranking them if we didn't have those guys. We then do cloud and shadow masking, because if I'm doing change detection between 2 images and one has a cloud in it, that gets flagged as a very abrupt thing, and we want to ignore that. Likewise, if there's snow in one scene and not another scene, that gets flagged as a change that it's not really the kind of change we're looking for in this event here. So, these clouds and these cloud shadows, they get in the way. And it's very algorithm dependent on, as far as change detection algorithm goes, is what you want to do with those. What do I do with the edges of the clouds where I can still see through the clouds, but the signal's been changed a little bit so that when I do a change detection, it flags something. My analysts that look at it say, don't mess with those, I need to see the change underneath, but yet it's getting flagged as a change. So it's kind of a fight. One analyst will say do it, one won't, and so it becomes an artifact still that you have to clean up. And I'll show you some shots of that in a minute. There's other projects as well that are searching for these types of ways to automatically detect clouds. So we put our heads together a little bit and come up with some methods for that. The current methods that we have, the ones that are out right now, are really good, but are they good enough? It's one of those things that when I show a stack to a scientist doing change or time series change analysis, they see the cloud screens and they think, wow, this is great. But after they use them a while, they're like, it could be a little better in this region, things like that. And to do them on a stack-by-stack basis with so many scenes, you really need an automated method to do that. Poor detections cause artifacts in your change detection product, and that needs to be cleaned up somehow, and in our case, usually manually cleaned up and edited. So you don't want too many of those, and it becomes how much are you going to include, how much are you going to exclude. Our methods are basically a cleanup of what comes out of the LADAP's surface reflectance processing software. They create a set of masks for clouds and dark targets, bright targets, things like that, with a combination of a algorithm written at Boston University called FMask. So we took both of those algorithms into account, and they are kind of the de facto algorithms these days. So this is a snip of a bunch of slides down to one here, but it basically shows you that we are grabbing clouds and their shadows and putting those in as a mask layer for a given scene. So now on to the change detection piece. After these corrections have been applied and we generate these masks, we calculate a common frame, we reproject to Albers. So now we have this data stack in a common projection in a common line sample grid. So we can go into our image processing packages and just scroll through these things and they'll all line up. There was a change detection algorithm called the multi-index integrated change analysis algorithm that was developed by the NLCD project. And what they wanted to do is detect change in land cover over a 5-year interval. So they would take images 5 years apart that were as close in date as they could and run this algorithm on it. And as a footnote to that, they were using a leaf off and a leaf on over this 5-year period. LANDFIRE wants to find changes that are more frequent than that, so we are using 2 scenes a year, a leaf on and a leaf off, roughly, for each year of that brackets our change year. So in this case, we're doing a 2010 update. We have scenes from 7, 8, 9, 10, 11. So it's kind of a move for NLCD and LANDFIRE to start sharing algorithms, tools, things like that. This is a diagram of what we do on a per path row basis. So you can see that we have leaf on and leaf off products for each of 5 years. My cursor's on the 2007 right here, then the 2008, 2009, 10, and 11. And we run a change pair between the leaf off pairs and calculate the results, and we get this change vector thing called MIICA. We get a difference in NBR, difference in NDVI, and a difference in a moisture index, and we store all that stuff off. And we end up doing all these combinations through the leaf on and leaf off periods. And we even do more than what is listed on this slide in that we do a skip a year thing as well, so we can fill in holes. We then take those pairs and start merging them into a summarized product. And this is all before we hit the analyst, so there's quite a stack of data that goes in before you even hit the analyst. So to give you a visual view, this is a pair that's going to be run into MIICA. There's a cloud bank here on the left side of the image with a shadow. And I should note that I developed these slides before we perfected our cloud shadow algorithm, and you'll see why we want a cloud shadow algorithm. This is the first scene in the change pair process. This is the second pair in the change pair process, second scene of the pair. And you can see there's some fire on the landscape that we're going to want to grab. We want to ignore the clouds, and we want to ignore the snow and ice. The change product that we get out of MIICA will basically say, look, do you have an increase in greenness or increase in vegetation, increase in brightness, I guess you should say, and or decrease. So you can see the burned areas do decrease and other areas increase. Now if you go back to this area where we had a cloud you can see right next to it where the cloud shadow was, where my cursor's at right now, is bright green. And so what that did is cause a false change, because once you look at this thing, you're saying, what is that? You know, oh, it was you have to go back and look, oh, it was a cloud shadow. And so if we mask those out, then that goes away. So like I said, this change detection output was done before we perfected the cloud mask. But you can see you've got various states of vegetation in these irrigated fields over here. The fire, the burn areas, the green up. Some of it's change we want to track, some of it is not, okay? And so what we're doing is we're handing our analysts a pretty big grab bag of change. And it hasn't been labeled yet, it's just that, hey, we noticed a change here and not here. Okay, but remember, we do a lot of these change pairs. So the images that I just showed you, we have change pair here, another one here, another one here, another one here, all the way two per year, okay? And so you start combining those to filter out the change that you do or you don't want to keep. What does the analyst do? The MIICA results that I was just talking about, enter this flowchart right here on the upper right. They then put that stack of results through a cleaning process that Jay and company call MIICA Clean, and they combine it with other things going on. They have refresh events from our events database that they rasterize and do some size thresholding on. They have some points from SmartFire that basically says, hey, we detected a start over here, that they use as a check. And of course, we have MTBS areas that will get into the mix, and they kind of lay all this stuff together, and they say, look, we have these known events in MTBS, we have these other refresh events that have probably happened. What can we do to label these things? What can we do to put these final products out? And so this is a hands-on process. We have a crew of 4 or 5 folks, hands-on, looking at this, looking at change, verifying the results, going through the MIICA stacks and saying, yes, okay, we're detecting a change here. This is probably what it is. I believe they're fairly conservative in marking the cause of an event, and if they don't have something in their database, unless they're absolutely sure about it, they'll mark it as an event but an unknown cause. So as an example of results, and these are very early results, we'll see an image down here in the lower left corner that has been masked, and you can see some of the mask artifacts showing up bright green that are probably not changed. They're probably mask artifacts, but we don't know. We have to go in and check. And then on the right, you can see the disturbance grid they arrived at. Now, what you're looking at on the left in the imagery, remember, is only one of 10 images that went into this process. So you can't always track a given change into an image just by showing it without actually scrolling through the things. So that, in a nutshell, is the MIICA process.